Hello, and thank you for coming to ISC's PDR. I'm Andrew Johnson, the current president of ISC and chief engineer of Project Phoenix.
I'm Jaden. I'm hardware lead. Oh, sorry. I'm Jaden Smith. I'm hardware lead and vice president.
I'm Jordan Krzan. I'm software lead.
I'm Andy Vega. I'm just another software member.
Awesome. And thank you for coming to our PDR. We are starting a few minutes late because I wanted to make sure everyone could log into our virtual meeting. But as you see, this will be a very quick PDR. We'll be looking to run about 30 or 40 minutes on presenting Project Phoenix, and then about 10 more minutes presenting Project TinyKart, and then we'll be having an open Q&A session at the end. So in this presentation, we'll be covering Project Phoenix and its subcomponents, along with the administrative changes that have been made to ISC, and along with introducing our newest, one of our new platforms, TinyKart. No. Awesome. So first thing I want to do was take a look into the past. One thing that's kind of special about ISC, unlike other teams, is that unlike formula teams and MASA that are all based around a specific competition, ISC is more based around an idea. The idea of autonomous vehicles and learning how to control them and how to get them to navigate various spaces. Since 2002, we have had 9 different competition teams across 4 different competitions, holding 17 top 3 finishes, 2 of which were first place finishes, and over 100 alumni that all came together with the same idea of working in the autonomous vehicle field. So with that, we'll be moving forward in a new era of ISC, unveiling our newest project, Project Phoenix. Project Phoenix is going to be a fully electric go-kart that is being converted to compete in the EV Autonomous Challenge in mid-May. EV Autonomous is a autonomous time trial style spec race that was started in 2019 at Purdue, which has participants like University of Pennsylvania, UC Berkeley, University of Hawaii. And although currently we're in a time trial style competition, there are plans to move this to full wheel-to-wheel racing with fully autonomous cars. We're looking to field somewhere between 3 to 5 for our initial phase and move up from there.
All right, so I'm going to jump into the mechanical systems. This is a spec race, which means all teams have the same platform. Woo. All right, we're good. Our steering motor is a Globe Motor Gen 5 Globe Power Steer EPAS motor. Our brake actuator is a CarTech CAN-enabled linear actuator, and then I'm going to go into a little bit about additional mounting for sensors and electronics, as well as some modifications to the battery box for safety and other things. There we go. So this is the spec cart. The motor is a Moto Energy 1907 48 volt kilowatt brushed motor. All teams get the same. In the future, if we do want to upgrade it, we may upgrade to a brushless motor, because right now our cap is around 30 miles per hour for speed. For batteries, we have 4 lead acid 12 volt batteries. Our motor controller is an all-tracks 24 to 48 DC motor controller, and then we have hydraulic brakes. This is our steering motor. So an input shaft connects the steering wheel to a gearbox, which takes the torque measurements from the driver's steering input and converts them to an output which actually moves the wheels. It has a built-in CAN receiver and is mounted by bolting a custom bracket to the cart frame. So some data is it runs optimally from 9 to 16 volts at around 13.5 amps, 50 newton meters of torque, and it runs around 525 degrees per second, which would mean that we could make a full turn without any weight at around a quarter second. It also runs at 500,000 baud CAN rate. For our brake actuator, it has a built-in microprocessor, and this will be mounted near the pivot point of our hydraulic brake arm to do electric braking, which will be trained by the AI. This operates around 250,000 baud rate, which is a bit lower, but this will be controlled by the microcontroller connected to this. It operates from around 10 to 30 volts with 5.8 amps at a max draw. Its max extension is 13.1 inches, and at around 50 pounds load, it can extend around 1.77 inches per second. This means that we can have fully locked brakes within around 3/4 of a second, which is pretty fast. Since electrical braking could have failure issues, we also have a mechanical band brake as a hardware-based braking system. So this happens where it's controlled by electromagnet, which gives us two options. We can either manually cut the power by using a circuit, or if the entire power circuit loses power, it'll automatically close the brake, which stops the car, regardless of the fact if the computer is working or not. For mounting, we've got a couple different things. We have the back shelf, which is welded aluminum, which will hold excess circuitry and other components. We have the camera and LiDAR mounting, which you can see here. It's vibration-resistant camera mounts that we bought, and then we'll bolt directly to mounting brackets that we have bolted to the cart. And we have also made computer and LiDAR cages to protect our more sensitive components from debris and impact if that ever happens. The cages you can see here at the bottom. We also are mounting our computer next to the driver using rubber-coated U-bolts. This helps with reducing vibration, which could potentially harm the computer. Top left, we have the microcontroller casing. These are 3D printed containers which protect the Teensies and our other microcontrollers from debris and water if that ever happens. These will be mounted close to their respective component to reduce the need for intense wire harnessing. And all of these components will not be welded to the cart, such as the frame, because this will make modifications in the future more difficult. So for battery storage, we have two types of battery, of LiPo and lead acid. For LiPo batteries, we will make compartments that will go right here next to the battery box. This will allow for easy storage and protection of the LiPos. For the lead acid battery box, the current ones that we have are not the best design, so we will be improving this design. We will cover it first for water resistance, and they'll also be able to be bolted on and taken off, which reduces the weight for mobility for the car by a lot, because you have 4 22-pound batteries, which if those can be taken off, the car can be moved much easier. So these are the sensors that we're using, which we'll go into a little bit more detail on the use of these a little bit later. But we have the Oak DS2 camera, which is a fixed focus stereo camera. This is the main source of perception for Phoenix and what we'll be used to train the AI. We also have the InnoMaker Mini 360-degree LiDAR. This is what we will use as the perception for AEB. So this will be mounted directly to the front of the cart, closest to where the impact will be. And this is around a 12-meter range, so it can see a little bit farther out than the camera can. We will also be using wheelocoders for odometry as well.
So for the electrical systems on this vehicle, it'll be a combination of spec circuits that were given to us by TinyKart USA, which we are required to use for our powertrain, along with mid and low voltage circuits that will be designed by members here in ISC. The first one is our 84-volt high voltage circuit. This one is the spec one provided by TinyKart. It is powered by the 4 sealed lead acid 12-volt batteries that give us a total spec of 48 volts, 35 amp hours, and weigh about 80 pounds. This circuit is primarily made of 2-gauge multi-strand wire that's able to comfortably carry the 52-volt, 120 amp max load that could be on these wires. And this includes our motor controller and our e-stop systems. Most of them will be on this power circuit because it is what is driving the motors. Our second, which is our mid-voltage system, is going to be powered by 3 22.2 6,000 milliamp hour 6S LiPo batteries that are all in parallel, giving us a total battery pack value of 22.2 volts, and that should actually say 18 amp hours at 3.6 pounds. You can see some rough estimations we made for our power consumption that led us to this battery type. One of the things with our system is that if we need to add and remove objects from this circuit, or if we need to replace them, let's say we got a new steering motor or brake actuator, we can easily manipulate what batteries are in this circuit based on what is required for our circuit. And then as for the boards, all of our boards are going to be powered by a separate 5-volt low voltage system. For our main interface, we're using an STM32 nuclear board that, unlike the TNC, actually has a built-in DAC and onboard Ethernet, and has 3.3 to 5 volt power supply pins. And then for our main CAN bus nodes, we'll be using TNC 4.1 Cortex processors.
Yeah. All right. So the software this year is going to be quite different looking than previous years of ISC, simply because we've changed competitions, and so the context has changed quite a bit. So the biggest thing you're going to notice, and just this at a very high level, is that we aren't going to be using the traditional nav stack anymore, at least for this year's implementation. And instead, we're actually just going to be abstracting all of that with a end-to-end behavior cloning neural network. So that'll be our primary form of control instead of the classic, you have LiDAR scans, build a map, plan on that map kind of approach that we've used for previous competitions, largely just because of the competition itself. I'll get into that more later. But at a high level, you can see we actually have pretty few inputs in general. Mainly when we're actually running the system, the only input that's going to be used for control is simply the camera. And that's because ahead of time, we're going to need to train the neural network using the as was mentioned, the hardware portion. We have the drive-by and brake-by wire systems, which will be able to encode those values. And then the AEB is just going to take steering encoder and the little LiDAR, which we have dubbed the baby LiDAR, into it. But again, just at a high level, we only have two forms of control for Phoenix, that being the neural network and the automatic emergency braking system, both of which we'll get into as we go further. Another thing that you'll see shortly is that a lot of our software this year is actually going to be embedded, not necessarily at in ROS, as is pretty usual for our projects. So I believe more on that can be here.
Yeah, so just a quick overview of the low-level embedded software that we're going to be running on the car. Of course, in past competitions, we've used motor controllers that have abstracted away most of this from us, so braking, turning, and throttle were all in one box. Now, with a hydraulic brake system and an individual ESC we have to control, we have to split that up. So we're going to be using a CAN bus to communicate with everything. So this is the CAN bus overview. So we're going to have an ECU for throttle, brake, and then the glow bar power steer, which has its own built-in CAN interface. And we'll be using a TNC that will be connected to the PC via UART to take control messages from the neural network and send it out onto the CAN bus. And yeah. So for our CAN network, we'll be using CAN 2.0B as it provides enough data for us to do what we need to do with it without finagling with CAN FD. We'll be using both a high and low priority bus for the high being for control, so steering, throttle, and braking, and then the low priority bus will be for encoder values and other sensor data that we need to send back to the PC. And then all the drive-by systems will be connected to the bus, but not only for Autom, but also for teleop, as we'll get into a little bit. We'll need to be able to record the values that a human driver is inputting into the car while it's being driven around to train the model. So we'll be using the ECUs for that as well and sending that information back to the PC. We'll currently be targeting 220 messages per second max on each bus for 50% utilization at 500K baud.
All right, so kind of the headlining feature of the software, as I mentioned before, was the end-to-end behavior cloning. So essentially the idea of what we're trying to do here is be able to have someone drive the cart, collect their data, and then have the cart drive as if they were driving it. So essentially cloning their behavior. So it's kind of in the name. But more specifically, the goal of the system isn't to replace, for instance, a traditional navigation stack to be like a general obstacle avoidance issue, or like obstacle avoidance algorithm, because that isn't as big of a focus this year since we're in a time trial format. So this year's competition, because we're just on an open track, is a bit more of a control-oriented competition, which is why this makes a bit more sense for what we're doing. Now, to implement this, we've actually partnered with a lab here at U of M Dearborn, that being BIMI, led by Dr. J.R. Kwan, if you know him. And so we're going to be helping integrate their end-to-end platform onto our platform. And so what you'll see is us doing things like porting that from ROS 1 to ROS 2, since that's still in ROS 1. We're going to need to make a simulation environment for that, since we're going to need to essentially emulate the track. We'll get into that more later. And we're also going to be just generally assisting with testing, data collection, the normal machine learning techniques, and that's going to be really nice to give our team some more exposure to those as well. Now, I have stolen this slide from the BIMI presentation, but this is the general idea of the neural network, essentially, as I mentioned before, human driver drives it. We'll collect tagged data, so we'll be recording the camera, the image, and then alongside the image, we'll also tag the steering values at the time, the throttle values at the time, and the brake values at that time. Then later we can go back to the lab, throw these onto a computer, train an initial model off that, and then I'll get into the training more later. But then essentially, once we've trained that to a degree which we're satisfied, we'll deploy that to the card in an actual competition environment. In that environment, we'll only need the camera input. So that'll be the primary perception mechanism, is just the camera image. And then given that image, we'll infer whether what's the appropriate braking, throttle, and steering values to remain on the course, and preferably have things like proper driving lines and such inferred from a good kart driver driving on the track in the first place. And so some advantages of this compared to the old methods that I mentioned is, for example, since our goal is to stay on the track, we don't have to do manual feature extraction to try and find what is the lines of the track. It'll learn that for us, which is useful because that can prevent issues like, as we found in IGVC last year, where we also had to do line detection of things like glare or shadows causing the lines to disappear. This will be able to handle a lot more of those extraneous situations, assuming we train it correctly, of course. So for the training, we're going to be using a method BIMI has been doing some research on. So instead of simply collecting a ton of data with the cart, which we will be doing, but instead of collecting an enormous amount of data from the cart to actually train it, we'll be using a method to generate our own simulated data. So essentially, the idea is we'll be running the cart, getting that labeled data, generating an initial model that's good enough, and then what we're going to do is deploy that model to sim. And in sim, it's going to do essentially what we did in real life, just in that simulated environment. So essentially, we'll be taking the outputs of the model and having it roll around sim, collect new data, label that new data, then we'll go in and manually trim out the parts of that data that are bad. So let's say it randomly swerves when right when it's supposed to going left. If we trim that out, we then retrain the model, then complete this loop. Theoretically, we'll be able to filter out a lot of the bad behaviors, given we had a reasonable model to start with. And what this should do is allow us to train the cart without needing to constantly gather new data, which is going to be very important since it's, we can't just roll this around like a snowplow in a parking lot. We need a track. So it's going to be a lot harder for us to just go out and test the cart this year. So it's important that we're able to train this, more efficiently.
So, as was just mentioned, we do need a simulation environment to be able to have the model train itself. So we'll be utilizing Ignition Gazebo to achieve this. It's proven well for us in the past with Ohm. So we, are going to go back to it so that we can simulate the actual physical dynamics of Phoenix, which will allow us to ease testing as it's considerably harder. As Andy mentioned, we can't just roll it out in the parking lot because that's not really the same environment. It's going to be competing on a go-kart track compared to things like Ohm or Yeti, which would have competed in environments that are similar enough to what we have access to here. So new to this year was track generation. So we're going to be using a plugin called Blender GIS, which is a fantastic plugin that allows us to grab satellite data of a region and create a elevation and accurate model of an area. So we can do this to get an actual one-to-one scale replica of the track that we'll be competing on, so that the AI can train itself on actual competition course, which will help us for several reasons, being able to train around things like pit road. What do you do when you approach pit road? Do you go down the pit or continue on the track? We'll be able to create a model that will be competition ready, and will give us an idea early on of any issues that we're going to run into at competition, potentially with the track, like if it takes one corner really bad consistently, things like that.
So something you may have noticed is that, as I mentioned, our end-to-end model is essentially going to be really like a lane keep in a way, and that it's just trying to stay on the track. We aren't going to be specifically tailoring it to obstacle avoidance, which does lead to an issue of, even though it isn't necessarily in our competition domain for there to be something jumping onto the track, we still want the cart to stop if there's something on the track, or just in general if the AI doesn't do what we think it will, because that's one of the issues of using machine learning, is that there are edge cases and it's very hard to test for every individual image that it could ever see. So what we want to do is to be able to have the cart preferably stop itself before it hits something. Now, we do have the e-stop that will always be there. However, relying purely on this kind of takes away from the autonomy, I suppose, of the vehicle. But also, it's not always practical. Sometimes you don't have time to react to the cart suddenly swerving. As such, we are developing an automatic emergency braking system to mitigate these concerns. And this is something that you see in actual vehicles, which I find interesting because we're essentially behavior cloning a human. Yet we've also behavior cloned some of the problems of humans, so it makes sense to copy some of the solutions as well. So essentially the idea of the system will be if the cart is heading towards something such that it'll collide in a time period that we aren't comfortable with, we'll probably end up defining this empirically using like stopping distances. And then we'll just e-stop the cart. That band brake from earlier will come into action, and then the cart will stop, hopefully without damaging anything or anyone. And then, as well, we won't be implementing this in ROS. This will be on a real-time system, since this also helps with the fact that ROS isn't real-time. So, for example, it runs out of RAM, just GPU issue, something like that. We won't just blindly start moving across the track. If we, swerve in something, we should stop automatically, which should help improve safety dramatically. So this is very briefly an overview of the current iteration of the algorithm we're choosing to use. This has gone through a few design revisions. I'm sure it will go through more. But essentially, the idea of what we're doing right now is taking a 2D LiDAR rather than like a radar, which you would find on some, like, in production cars. But we're taking a 2D LiDAR, essentially taking points we get out of that, filling a grid where each of those grid squares says if there's something like an obstacle there or not. We'll then be predicting, given the current cart's parameters, the trajectory of where that cart will go, so essentially from like an arc. And then what we're going to do is basically iterate over certain time steps on that arc. And for each of those time steps, we'll find like a collision box around the cart. So we'll just measure that, basically just make a big box around the cart. Then what we'll go and we'll fill in the grid squares that box is overlaying. If any of those grid squares are already filled by an obstacle, then we know that would be a collision. We complete this process until, since we're essentially integrating over a physics function that's with time, we can just do this until we hit our maximum time to collision value. If we have any overlapping squares, we know that's going to be collision. We then e-stop, and then collision avoided. So even with this current form, there are some design considerations that we're still working through. One, we're currently relying only on one sensor, being the little LiDAR. We'll have to see how noisy this is in the real-world environment. It may be worth it to look into sensor fusion with perhaps even a different thing than another laser that could help through some of that error. That's something we'll have to see. And then second, the motion model right now, since we aren't given a path from the end to end, like I mentioned earlier, this is essentially like there's an individual behind the wheel, and in fact, this AEB could be run with an individual behind the wheel, even. So we aren't able to know the exact path the cart's going to take, so we have to predict that. Currently, we're holding a lot of things constant, essentially just everything's constant, including velocity. So we'll have to see. This may be too restrictive to be realistic in the real world. We might get a lot of false positives. So something we could do is attempt to use some more like classical machine learning to derive those paths. I do wonder if that is advised for the safety system. So that's just something we're currently working on. And if you have worked with this, I would be curious to see your thoughts or suggestions on this, since ultimately we're here to learn. I'm curious to see how this would be approached in a way that I haven't at the moment.
So going off of what Andy was talking about with safety, obviously safety is incredibly critical on a fast-moving platform like this. This go-kart's going to be weighing around about 200 pounds and moving 15 to 20 miles an hour is our current target. So in that case, F do really be equal to MA. So if it were to hit something, it would be rough. So we need to ensure that all of our embedded subsystems are very safe, especially considering that with our current training method of having someone drive the cart physically and also collecting data, that means that we're going to have to abstract a lot of things, especially the braking system, from the actual hydraulics themselves. So the user of the cart will be controlling a pedal that will be sending data to an ECU that will be controlling the hydraulic system and will not currently have direct control over the hydraulics, which, as I'm sure you all can see, has a few potential issues. So we have a couple things that we want to do to ensure that this will be safe. So we're going to have both onboard and wireless e-stops, like all of our other bots that will fire the band brake, as was talked about previously. if the PC to CAN interface board crashes, for example, during autonomous operation, you would lose all control. So we're going to set up a way so that if that does crash, it's going to immediately fire the e-stop, stopping the car. AEB, as Andy mentioned, will also stop the cart under e-stop if it deems it necessary. And should any other board fail and the operator is unable to react at the time if they are manually driving the cart, AEB should be able to ensure that, they won't suffer any kind of collision. And then finally, power loss will result in an e-stop because the electromagnetic band brake will be held open under power. So should the entire system run out of power, battery goes bad or something, it will result in the car immediately stopping. So these are just a couple of different things that we're going to implement, as well as some more as we continue to look at potential safety issues to ensure that, we don't end up like our friend in the corner right here going into a ditch. So yeah, with that.
Awesome. So, along with a restructuring of all of our projects, we have had an administrative restructure here on the team. The idea with this new team structure is being implemented is trying to promote more cohesion between the members of different sub-teams. One of the issues we found in previous ISC structures is that there was a lot of division between the software guys, the hardware guys, people who worked on Ohm, people who worked on Yeti. So by restructuring the leads and forcing a lot more cohesion between them, we're hoping to have a more cohesive team as a whole. And then, of course, in the corner, we have our little total member numbers that are always good to have. And then on top of that, we have a whole new suite of administrative tools, thanks to BAM. Hi, BAM. With two big things being a new BOM system. Basically, what this allows me to do is input things that we've purchased, how much they cost, how much was shipping, and then tracking how long did it actually take for the goods to get in. We're also comparing delivery times for different suppliers to see if there's one. Let's say we were in a crunch and we really need a part sooner. Who's more likely to actually deliver in a shorter period of time, people like McMaster-Carr versus Grainger versus Amazon and so on. This also auto-populates out into subcategories, allowing us to track, okay, how is electrical doing on budget, how is mechanical doing on budget, how are the sensors doing on budget, and how much do we have left to spend. So let's say we break one of our sensors. Do I have the budget left in my sensor budget from the pitch session to purchase new sensors, or do I have to go looking elsewhere? Maybe we need to cut and get cheaper batteries, stuff like that. The other thing, too, will be a integration of a new Gantt system. This Gantt chart is fully interactive, allows us to input different tasks. And then the important feature for me is the start and end dates. In this version of the graph, we have our TTF, or time till finished. And this kind of is a ticker letting us know how long do you have until this is due. So when you pull up this track, you can kind of see, this was pulled from today, our preliminary design date was shifted slightly, but we see we have like about 40 days-ish until the end of the semester, and about only 193 days until pre-comp review, and that ticks down slowly day by day. And there's actually a second version of this Gantt chart that we are building as we go. One thing we wanted to track is how long does it actually take to accomplish certain tasks. This is a completely different style of competition from years past, and we kind of just guessed on how long we thought it would take to build a drive-by-wire system, design a CAN bus, stuff like that. So there's actually a separate one that I'm filling out as tasks are actually started and completed, seeing how long did it take us to design this system and why. So we're leaving comments like, oh, it's taking us 4 weeks to mount the computers, but that's because Grainger keeps sending us the wrong parts and it's taking 2 weeks to ship each part, not because it was hard to design. But drive-by-wire, we're having holdups because it turns out there's only 2 suppliers in the country that want to give us steering motors, things like that. So when we make future projects, we'll be able to better predict how long it would take to complete each task and have better time management. Now, one of the things with autonomous racing that we found, and just autonomy in general, is holy crap, autonomy is hard. It can also be very daunting for new members to get into. So one of the things we wanted to do was create a smaller scale competition that would help the new members get integrated into autonomous racing. So we decided to create TinyKart. Why do I have to double click? That's so sad. So what is TinyKart? TinyKart is a small team-based learning program for Project Phoenix with an internal competition around April of 2023. Basically, teams will be, the new members of the team will be broken into sub-teams that will do small-scale autonomous vehicle design and develop over ideally 1 semester. And it'll be create a more accessible platform to allow members to develop and test basic mechanical, electrical, and software skills on a lot lower risk platform. Currently, our vehicle looks like it'll cost us about $25,000 to $30,000. Each one of our TinyKarts, including the onboard computers and sensors, should be just under $1,000, which is a lot more affordable for people to work on. And we also did take this inspiration from F-110 and Donkey Car.
A little bit more into the hardware of TinyKart. The platform that we will be using is a brushed two-wheel drive Traxxas Slash, which you can see here. Obviously, this is already built, so the mechanical side is pretty simple. Mechanical members will mostly just be designing a chassis to hold all of the components. The electrical teams, or the electrical parts of the team, will design a safety circuit, integrate a computation source, whether that's a microcomputer like you can see on this cart, or embedded microcontrollers. They'll also include sensors, a power circuit to power both the cart and the computation source, as well as microcontrollers. A little bit more on the software.
All right, so real quick, the current build of TinyKart Software, I really, preferably there wouldn't be a TinyKart Software. I'd prefer for this more to be like a DIY kind of competition, but right now, this kind of a vanilla TinyKart software package, which I built off of KiloOhm, which is built off of the last Yeti. So this is very similar to what ISC has been doing for quite a few years now. So it's basically just running a pretty standard Rust2 Galactic Nav2 stack, using A-Star as its global planner, WWB as its local control planner, Slam Toolbox for Slam. We're doing some sensor fusion with IMU, Ignition Gazebo Simulator. It's very similar to our past projects. Essentially, it should just be almost like TurtleBot. You look at it, this is a decent way to do it. It certainly has its flaws, but it does work. Ultimately, though, I'd really like each TinyKart team to preferably quickly drift away from this base to explore robotics a little. So something like everything from changing one of the planners to changing the entire slam to completely redoing portions to even abandoning ROS entirely if they want. But that's kind of philosophy I'd like to take towards TinyKart as a it's for learning. There is a competition, but ultimately it should be about exploration first more than anything. And that continues with the embedded stuff because we need an embedded controller to connect to the ESC on the cart. And right now that's all it does. You could of course add other things, even just RGB or something. So right now we're using little Raspberry Pi Picos. I think these are pretty great for this purpose because one, they're really cheap, but two, they have a ton of software libraries for it and a ton of documentation for those. So everything from its built-in library, but also Arduino. It even has a free RTOS port. You can do a lot with these little things, and that should provide a strong jumping-off point for people getting into embedded development, just as much as autonomous vehicles or hopefully electrical as well.
Awesome. And that concludes our PDR presentation. We will be open for questions. If you are virtual, I will ask that you try to use the raise hand feature. We don't have the best speaker system here, so I might have to just rattle this off from my earbud. But I guess I will start. Any questions from in person? Yes, Trevor.
For the band braking system, does it slow the cart down gradually or immediately apply and lock up?
So currently, we actually don't have the band brake system. We can buy different band brakes that would allow us to control if it would be a gradual stop or a full lockup. Ideally, we want it to be just below lockup. We have found that at our top speed, a complete lockup causes the cart to just turn at a 90-degree angle and skid across the pavement. But if we find that we're just a little bit below lockup point, which we'll be doing some testing on to figure out exactly how strong of a band brake we need, we find that we have a much better deceleration and actually uses a shorter distance.
Okay, that's what I was worried about, because if you just lock up the rear end, it's just going to spin around on itself.
Yeah, we did some pretty extensive testing, actually on one of your test days, looking to see what type of pressures and at what speed we should be expecting cart behavior to be at. We actually found that locking up at anything under 20 miles an hour, it stayed with good heading. But right now our top speed with the software is just north of 20, and if we hit that range and we lock up, we do a complete 90-degree turn and then skid sideways, which is less than ideal. Let's see, any questions? Oh, there is a question from Devin online. Oh, Hello, Sierra, speaking through Devin. Awesome. The question was if we could send out our slides. We will be sending out copies of the slides to everyone that was invited. That'll happen shortly after the completion of PDR. I know there was quite a few alumni that had asked for slides as well that weren't able to make it. Everyone will be getting a copy of the slides. Christian says he'll also send notes. Awesome. Are there any other questions from people who are in the virtual meeting? I will take that as a no. Trevor, you have another question.
In the event of loss of control, will the computer be able to self-correct or no? In the event of a lockup?
The event of a lockup, more potentially, it depends on how like if it were to start fishtailing, it could potentially correct itself, but under like a severe, like a spin out, no, it would be unable to correct itself.
Yeah, the in-person question was, in the event of a lockup, would the computer be able to correct itself? Currently, we do not believe so. We think if there's a fishtail, it could correct itself. But if it turns 90 degrees, one of the things that's full end-to-end, if it's never seen the image before, we would ideally e-stop it because we don't know how it would react. If it sees the track at a 90-degree angle, it has definitely never seen that before. We would not want it to attempt to correct that.
That is something as well that I'm interested to test out to see how common that is. If that's something that would just e-stop when it comes up, or if that's something we have to design on, because that is something I've considered. But right now, it's going to be a test and see if we need to design a specific solution to that problem in particular.
Yeah. Any other questions from in person?
Is the automatic emergency braking going to account for different surface tractions?
At the moment, no, just because I don't have a means to determine that.
What are you going to assume then in the meantime for your stopping braking?
So that's one of the reasons that right now I'm using time to collision as a metric. So that's something that we just have to, again, just empirically go out and test on preferably a track, but even the parking lot if we have to. Just get a reasonable value of, at the speed we expect to go at, probably at our maximum speed. And it's a given you don't find a way to do friction. Just at our maximum expected speed and, reasonably normal conditions, what is the stopping distance, determine the time to collision based off of that, and be a little more restricted than we have to. Preferably we find a way to implement slip, but at the moment, the algorithm just has a set time to collision value.
I don't know if you got that virtually. The in-person question was, do we have a way to calculate based on track material? And currently, we're going to collect data based on the service we have here at UMD, and then collect new numbers once we get to the track. But it is not adaptive for slippage. All right. Any other questions in person? Trevor.
Just going off of what Carmen said, would you guys consider having multiple strength bands available? So you're testing on like our track out here where it's super slick from the top new seal coat, and then go to a concrete track where you're going to have more grip. If you need to go to a stronger band or a lesser band, would that be a consideration? Just depending on having different options for surface type.
Yeah, that's a good question. The question was, will we have different bands to adapt to different materials? That is definitely something we can do. Band brakes are not that expensive. The main thing we just have to discuss is being emergency braking. I don't know how much adapting the last-minute brake would help with stopping. If it's e-braking, it's gonna be a little chaotic. But it's definitely something that we can have. Band brakes are not expensive. Are there any questions from the virtual party? No? Any questions from in person? Jacob.
Do you anticipate any issues where you may have wheel slip and might need to integrate some sort of way of calculating whether or not you have that in order for either braking or acceleration differences based on track surfaces and whatnot?
That's definitely something that, like I've mentioned a few times, is at the moment I'm taking as a let's test it and see, because that should be something our algorithms are amendable to. But right now, that's just extra complexity. I don't want to have to integrate if we don't have to. but that's definitely something that may come up. And we'll have to see. It's a little unfortunate just because we have a solid rear axle, and then the way the drive wheels work on the go-kart is, of course, it lifts one of the wheels up. So it's a little difficult to just do that with encoders like you may normally do. So you'd have to see how we'd even detect that.
Yep.
That's if that comes up, that is something we may have to work on.
Awesome. Any more questions in person? Josh.
So, first of all, please add slide numbers.
It's hard to make comments on slides.
No.
So you didn't want me to put slide comments, I see. I guess one thing I was going to ask is, so I see on your like low level like software diagrams, if you talk about your different like control units or whatever, what sort of like your different vehicle control units or so on and so forth, but what sort of actual like hardware design has been made on any of them? Like, at least because it seems like the only time they were like mentioned as separate units was in this slide. Like, is what kind of like other, for example, like, basically like what kind of schematic or like hardware design has been made for, and additionally, how do you plan on putting the individual like ECUs, VCUs, and all that stuff together?
So at the moment, the each of the ECUs are just a single microcontroller with a CAN transceiver to communicate onto the bus. With the, well, yeah, that's essentially what all of them are. The only thing that's really of note is the interface board, which will have a switch on it that will allow, if a human driver is going to collect data, to switch it in order so that it will so that it'll actually start doing the actual collection instead of attempting to send control messages, as well as I'm sure you can see the e-stop connectivity of the interface board. Continuing on, this was something that I didn't talk about a whole lot on this slide because I was trying to keep pace, but the each of the brake and throttle ECUs are going to have the stock 0 to 5 kilo ohm throttle pedal on. So the go-kart, the throttle pedal on the go-kart is just a 0 to 5 kilo ohm potentiometer. So we're just going to be using 2 of those in order to get values for throttle position from each of the throttle and brake pedal, and then the glow bar power steer unit does that internally, so we don't have to do anything there. That's all one unit.
I also hate to be that guy, but this is more of a hardware diagram than a software diagram.
Yeah, we designed it more. That is true. We designed it more of like a logic level. What's networked to what, or like what's input
That's
output.
fine. That's something you definitely have.
Yeah.
Yeah.
Just
No, that's
wanted to say that.
Yeah.
And
I guess one other thing going on top of that is, where do you, so it seems like there's just a little dedicated platform for just all the electronics, it sounds like, from at least the one thing that I saw on the one slide. Yeah, just that little section there. At least part of my I'm still new in the automotive electronic industry myself, but from what I understand, part of the reason why a lot of the different things are separated and separate, like different logical units, is because they have to be separated into like different parts of the car, and there's like different, like a lot of stuff for each of them. But for some of the low level stuff like this, I wonder if you might be able to combine like 1 or 2 of those different things together. Bam, I'm sure will stop me and interrupt me if I'm saying something wrong, but I guess to me it seems a little illogical having 4 different microcontrollers running basically 2 inches from each other, even if they are doing like different things.
Bam. Yeah, that's true. We could definitely condense this down a little more. We just wanted to, partially, some of this stuff like the brake actuator and the glow bar power steer, those happen separate, but the we're just also keeps all of our eggs out of one basket per se. So if one of these does fail, it at least won't. It only kills like 1 or 2 functions, ideally. So, I mean, that was sort of the design. We can definitely go back and see if we can merge a couple of these together, because it would improve on.
'Cause I know if you plan on using that Nuclear 144 board, you have 1,000,001 pins. I'm not saying you have to put everything on that. You can still have your separate ones, but I would just hate to see the whole you spend $30 on the nice big, microcontroller dev kit, and you only use just the DAC output from it.
That's true. Yeah,
And
that's a
also
fair.
another thing I want to mention about that is, are you sure the motor controller requires a DAC output, or if it can work with a PWM output where it averages to get that output? Because that's what happens a lot of time in software. Basically, it will have like a 50% duty cycle, but it will read it as if it's like 2.5 volts versus 5.
You would have to we have to double check the settings on the ESC itself. As at the moment we know that it can take 0 to 5 volt. There are a number of other throttle control settings on it though, so I'm pretty sure it can take PWM in. So we could look at that as well.
It actually can't. So it can't take PWM in like the sense of like an RC car controller. If you're talking about like PWM low pass filter shenanigans to do
I'm not talking about PWM in the sense of an RC car. I'm talking about just PWM 100% duty cycles 5 volts, 50% duty cycle averages 2.5, and so on and so forth.
Yeah, a lot of that as well is just going to fall on the electrical side. Frankly, that's a bit beyond my knowledge.
I guess
but
that'd be
it may be
something
possible.
to, especially test, because that would make something a lot simpler. 'Cause,
Any more questions? Virtual or in person? Last call.
make sure to email you the slides.
I will email everyone the slides with slide numbers.
Please put numbers.
All right. Well, that completes ISC's PDR. Thank you for coming.
Oh wait, actually, I have one more.
Oh, he has one more thing.
Yeah. So at the end here, I have QR codes.
Oh.
If you don't know, we have a. I don't know if I can hear. I guess if you don't know, we have a YouTube channel. We upload tutorial stuff mainly, but if we do cool stuff with the car, we'll probably take a video of it and upload it. So if you want to keep up to date with what we're doing, that's there. Also, for the software side of things, we have a specific GitHub org for Phoenix, just to keep it organized, since we're going to have a lot of individual code bases for specifically this project. So that's also there if you're more into software, want to see what we're doing. We also have our current software design docs up there that we're hopefully going to be keeping up to date. If you just want to keep up to date with what we're doing.
Like and subscribe. Like and subscribe.
Please like and subscribe.
Ring that bell icon.
All right. Well, thank you.
Where's your Twitter? What the hell?